Hi everyone. In this video I'll be explaining about the nitration of benzene mechanism. So this mechanism, it uses or it involves two strong acids. So right here we have HNO3 and also H2SO4. So before I move on, I also learned that this also has another name due to this right here. So I think I made a mistake right here, but let me fix it real quick. So this is supposed to be a benzene ring, right? So this benzene ring actually has H atom attached to it. However, in this mechanism, we will replace the H atom with NO2, which is an electrophile. So the other name is called electrophilic aromatic substitution. And again, I made a mistake right there. So that's the other name. So I will explain this accordingly or in sequence, or basically just in steps, so that we can understand this together better. So in this first step, the hydrogen ion H plus from the sulfuric acid, which is H2SO4. So right here is H2SO4 right here, but I will not draw anything on it. So will be transferred to nitric acid, which is HNO3. This part right here. Okay. So as a catalyst, sulfuric acid will facilitate the reaction by providing a medium conducive to proton transfer, but does not become a direct participant in the overall reaction. So let me highlight right here. I've highlighted it, however. So one of the lone pairs on the O atom of the HNO3 will attack the more electronegative H atom on the H2SO4. Sorry. So on the H2SO4, the sigma bond between the H atom and the O atom will break, and both will be pushed toward the more electronegative O atom, and this process will form H2NO3 with positive charge, and also H negative. So sorry, I'm kind of confused. SO4H H2SO4. I'm so sorry for the confusion, and I'm so sorry about the background noise because there's a moss near to us right here right now. So moving on, now the sigma bond between the positive NO3 is weak and will break the release of H2O, which we all know this is a good living group. So the both electrons in the sigma bond are pushed toward the O atom, as it is more electronegative than the N atom. How would I do this? I think I should highlight it like this, I guess. Okay. And then now let's move to the bottom part right here. So the protonation step, not protonation, proton ion, protonation. Alright, we're back. So it is called protonation. So this step, it forms the natrium ion, which is NO2 plus, and the bisulfate ion, which the one I also struggled to pronounce earlier, which is the negative charge, is HSO4. So the nitronium ion, which is electrophile, is responsible for the electrophilic aromatic substitution reaction with benzene, which I mentioned earlier, which is this electrophilic aromatic substitution reaction. So as you can see, we have natrium ion, which is the electrophile in this mechanism. Now moving on to the next step. So in this step, the benzene ring will act as a nucleophile with it the localized pi bond pi electron cloud. So the electron-rich region of the benzene ring is attracted to the positively. Let's just make it short. So basically, what the benzene ring gonna do is gonna attack this end right here, because it is more what do we call this? More electropositive. Therefore, it will attack more electrophile, in a simple term, I guess. So, the benzene and the other aromatic compounds are highly stable due to their delocalized pi electron system, which provides significant aromatic stabilization, breaking this aromaticity by forming the omega complex, which required substantial energy, making it a slow process. A slow process. I think I should highlight that. Yep. Now, what happened? What happened next? Exactly. So what happened next is the electrophile bonds with one of the benzene ring's carbon atoms will break the ring's aromaticity. This results in the formation of a, a sigma complex. This intermediate is often represented as an uranium ion, where the positive charge is delocalized over the benzene ring. So the uranium ion is a resonance stabilized carbocation ion intermediate. The positive charge in the uranium ion is delocalized over the aromatic ring through resonance, resulting in multiple resonance structures in these resonance structures. So I also learned that, and because it attacks the end right here, right here. So what's gonna happen is there's gonna be two atoms attached to the benzene ring, and at the benzene ring itself, it's gonna be positive charge right here, and also actually there's like another here with double bond O and one single bond O, which right here we're gonna have three lone pairs, and it is gonna give you only two lone pairs, and right here is gonna be positive charge. Yeah, that's what I learned from a video on YouTube, but I don't know if it's correct. Yeah, but yeah, I hope I get the concept correct. Yeah, so these three, what are they called actually? These are called as uranium ions. Yes. So last but not least, we have finally reached the final step of this whole mechanism. I think, yeah, it is. So in this step 3, it is called the deprotonation of uranium ions. So after the formation of uranium ion, which is a positively charged carbon atoms, is within the benzene ring, this positively charged carbon atom is often adjacent to a hydrogen atom on one of the ring carbons. So the negatively charged, which is the negative charge, HSO4 ion, will act as a base and abstract a proton from the carbon atom, which was adjacent to the positively charged carbon atom in the uranium ion. I think I should zoom in and give you guys a closure, yeah? So, right here, and also the positive charge at the benzene ring itself. Okay? Now, the proton transfer forms a double bond between the carbon atoms, restoring the ring's aromaticity, and this step also involves donating electrons from the carbon-hydrogen bond to the positively charged carbon atom, forming a new pi bond. Right. Now, the product. The product is this. So the formation of the double bond effectively restores the aromatic character of the ring, completing the re-aromatization process. The resulting intermediate is often a substitute aromatic compound where the electrophile has been incorporated into the ring. In this case, we call it as nitrobenzene, as we can see from the early part of my video. So in the nitration of benzene, H2SO4 will act as a catalyst, and therefore at the end of the reaction the structure of H2SO4 is recovered. And I also learned on YouTube video from this particular channel where I think everyone watched them for chemistry. The byproduct also involve H2O, but I'm not sure. I'm gonna reconfirm this with Sir Byron anytime around. I think that is all from me. I think this is the longest video I've ever recorded for mechanistic reasoning, but I had fun. So that's all for me. Thank you and goodbye.